So I'd like to spend some time on the design rule set. Okay, how the rules are established. Actually, let's say, after what you have seen of the fabrication process, you can imagine that there are some possibilities that the fabrication process has and some possibilities that it does not have. And in order to be able to properly fabricate the integrated circuit, the process engineers have to provide some rules to the circuit designers. And they have to be satisfied. In which terms? There are two different types of rules. One very so the most important aspect is that there's a minimum line width that depends on lithography and process. And this minimum line width is the minimum feature size that can be obtained for any different type of layer. For example, when we obtain the gate stack, so the gate insulator and the top polysilicon and the silicide on top, then the lithographic process is able to obtain a minimum length of the gate, which is the minimum line width of the gate stack, and this has to be defined and provided to the designer. And we also have micron rules. So one set of rules is the minimum line width for different types of layers, and the other set of rules is the so-called micron rules, which are the absolute dimensions for intra-layer and inter-layer layouts. And this actually is something that is not really connected to lithography and process, but is something that is more related to the alignment of the different layers. Because, of course, the alignment is not perfect, and therefore, if you want to have two different types of layers not overlapping, you need to put a minimum distance that also takes into account the tolerance that you have on the positioning of the layers. So, for example, just to have an idea, if we consider a CMOS process relatively old as of now, a 0.25 micron process, in that years, 0.25 micron means that the minimum gate length in those transistors is 0.25. So in a 0.25 micron process, we have 5 different types of layers, of metal layers, from metal 1 to metal 5. We have only one well, only the N well is a single well process. Then we have another layer for the polysilicon. Then we have layers for the contacts for the vias, for the active areas, and this is for M plus and P plus are additional doping layers. I mean, this last row is not as important as the other ones. Now, for every single layer, there are intra-layer design rules, and they are related to lithography and process. For example, in this 0.25 micron process, the metal 1, M1 layer, cannot be thinner than 0.32 micron, and the separation between two different metal layers has to be at least, metal lines has to be at least 0.25 microns. Okay. From this example, you can easily understand that the limit is given by lithography and by the following process, because in order to define two metal lines which are separated by 0.32 micron, you need to have a proper lithography and proper etching of the excess metal that you put. What exactly does the design rule mean? That if the separation between two metal lines is smaller than 0.32 micron, you could simply have only one, let's say, joint metal line. Okay? There's no guarantee on the separation of the two metal lines. Or, from another point of view, if you try to do a metal line which is narrower than 0.32 micron, you can end up with a metal line which is interrupted, because at some point let's say at some point along the metal line you could have a zero thickness. Okay, so these are minimum feature size, because of course there are irregularities, and you have these design rules for every different type of layer. For the metal, for example, for the polysilicon, you have minimum 0.24 micron, which is the minimum gate length, and the separation of at least 0.36 micron, and so on. This is one set of rules. Then there is another set of rules which is related to the interaction between two different types of layers. For example, in this case, we have the poly layer, which in a transistor, you know, defines the gate, and the P plus region, which in a transistor defines the essentially, if it's a PMOS transistor, the bottom, let me use this, the bottom P plus region is, for example, the source region, and the top P plus region is the drain region. So the two P plus doped regions are source and drain, and the poly represents the gate. Now, in this case, for example, you need this, let's start from the simplest thing. This minimum distance of 0.36 micron between the end of the poly gate and the end of the P plus. And the reason for this is easy, because since you do not have a perfect alignment between the two layers, if for some reasons the polysilicon stops here instead of here because of errors and tolerances of alignment, you have here a short circuit between the drain and the source, because there is there's a P plus region which is connecting the drain and the source. Okay, so this is the and this, for example, in a typical situation would imply that you have to put the integrated circuit in the trash. It is something that reduces a lot the fabrication yield. And all the other, the reasons for all the other thing is similar. For example, you need at least 0.44 because you need to be sure that the P plus does not end in the middle of the poly, because otherwise you do not have, for example, a source contact anymore. Okay? So all these other rules have to be satisfied by the designer at the point of providing the layout to the fabrication plant. Otherwise, there is no guarantee that there is no possibility that the integrated circuit works. You still have never a guarantee, but if you do not satisfy, typically if you do not satisfy these rules, the fabrication plant will not accept the design. And of course, we can continue. I just don't want to show you everything, but we need to have different rules for any situation in which two layers are very strictly coupled. For example, in this case, you have contacts and bias. For example, you have poly and the metal, and you want to connect the poly with the metal through, this is a via. You have to make a hole in the poly and in the metal, and to put tungsten typically in the hole, tungsten as a good conductor. Of course, you need to be sure that everything is aligned. The layer of tungsten, the layer of poly, and the layer of the metal are aligned, and in order to guarantee that the alignment is good, you need to let's say, have this region of poly, this square of poly, in which you have to make the hole larger than the size of the hole by at least 0.14 micron for the poly and 0.09 micron for the metal. Okay, these are all measures that are made to ensure that at the end you really can have a good contact. Now, the important thing, I don't want to, of course, go into the details, because there are thousands of rules to be satisfied. And of course, in a proper design, you have, let's say, between millions and billions of transistors. So you can imagine the size of the effort. And of course, this is completely automated. So there's a code which is called design rule checker that receives as an input all the designs of all the layers and checks if all the rules are satisfied. This typically is done in the design center at the end of the design, after the circuit schematic. We've transformed the design from a circuit schematic into a layout on silicon, and then we need to run a design rule checker on the silicon. If the design passes the design rule checker, then it can be sent to the fab. This is a very important aspect. You need to consider that even if the design passes the design rule checker, there's no guarantee that it will work. But at least you have satisfied the minimum requirements to have a good probability that it will work. Okay? So it's really a set of minimum requirements that, of course, are constraining a lot the designer, especially for the advanced nodes, and if you want to have high-performing integrated circuits. Okay. Very quickly, the last aspect I want to touch is the one of packaging, because typically it's the only one that one can really see if one takes, let's say, an integrated circuit in the end. You only see the package. You do not see the integrated circuit that is inside. But actually, the package is a very sophisticated piece in the whole thing, because it serves several different purposes. First of all, it serves some electrical purposes, in the sense that it has to add low parasitics, so low parasitic components to the circuit. This is especially important if the integrated circuit that you want to build is a circuit with very high speed input and output. For example, if it's a radio, if it's a communication circuit, if it has a high speed data bus, you really need to put particular emphasis on the electrical properties of the package. Then, of course, the package has to provide the mechanical protection, and therefore it must be reliable and robust. And very important, it has to have some thermal function. In particular, it needs to enable an efficient removal of heat. This is extremely important. In many packages, you have let's say, some heat dissipation units. They are extremely important. In addition to all that, it must be cheap, because especially in relatively cheap integrated circuits, the the cost of the package is not negligible at all over the cost of the whole chip, compared to the cost of the whole chip. So one thing that I think requires some attention is this fact. As you have seen, at the end of a fabrication process, you have some small pieces of silicon, which are called die, D-I-E, that contain the complete chip. And this is, for example, a silicon die, this small rectangle here. The external contacts for input and output are typically placed here in regions that are called pads. These have to be connected to the outside world. And what you typically do is that with glue, you put the silicon die on the package, on the substrate of the package, that is here, and then the substrate of the package is connected to the external pins of the chip. And therefore, for each pad, you have to put a gold wire connecting the pad to the pin. This is done automatically, can be done manually, but of course in large volumes is done by an automatic machine. And it's the simpler situation, it's the simplest situation, but of course the point is that especially for high data rates, it is a problem because these wires have a significant inductance, so they introduce large parasitics. And that then can, for example, reduce the bandwidth of the communication channel by a lot. This is the simplest situation. Another situation which is cheaper and is commonly used when you have cheap integrated circuits, for example, as in the chips that are used for radio frequency identification and for cheap smart cards. You don't want to don't want to solder every die, and then one can use these polymer tapes in which the wires are already imprinted. So you see this is a tape, you have a hole in the tape for the chip. In the hole, this is the cross-section of the tape. In the internal part of the tape, you have this the end of the wires which are ready to be connected to the pad. So you put the die on the substrate, you put some soldered bumps, some small drops of soldering material, and then on top of it you put the tape in order to connect every pad to the corresponding wires. Okay? Then the other end of the wire can be connected to the corresponding pin in the of the package. So the advantage here is that you do not have to individually bond every pad to the pin, but you can just put a tape. Of course, it's less precise, but it's cheaper and it's fast because it's faster. Okay. From the point of view of the parasitics, there is a small difference because in this case the size of the wire can be tightly controlled. Also the geometry has been pre-done. It's not done every time. It's already prepared on the tape, so it is more or less under control. The other possibility is to, which is very common now, is this flip chip bonding. This is extremely common for the chips with a very high pin density and with a very high input-output data rate. You basically have a substrate of the package with all these metal metal lines already interconnected with the external pins. And then you basically flip the die, and you use, instead of wires, some solder bumps, which are drops of soldering material that connect the pads on the top here with the wires of the package. And so the nice part with this situation, this is a bit more expensive, but the nice part is that, of course, you do not have long wires for the connection between pad and pin, and so you do not have the parasitics, and you can have much denser, a much denser pad geometry. So in the end, for the same size of the die, you can have many more pins. Because when you do the wire, all the pads have to be on the periphery of the die. In this case, they can also be in the middle. Okay. Then, once you have the package, you need to put the package on the board, of course. And as you probably know, there are at least two ways of putting a component on the board. You can have a through-hole mounting, which is very basic. Basically, this pin it enters in this hole on the board, and then you have some soldering material in order to put the pin to have the electrical and the mechanical soldering. Or you can have a surface mount situation in which you do not have through holes, but simply the pin is on just one surface. Of course, the advantage of this situation is that you typically can have much denser pins, and also you can have chips on both sides of the board. Otherwise, in this case, of course, you typically cannot use one side of the board. And these are, I just want to close with this, these are a few packages. This is probably the simplest one. It's called dual inline. So in the dual inline, let me just see if I can use the red at least here. Yeah. No. This is dual inline package. And here you have the die in the middle. On the periphery, you have the pads. You have a wire bonding for each pad to the pin, and the pins are on the longer sides of the package. On one line is here, and the other line is on the other side. This is pretty common. And another very common situation now is this one, the pin grid array. Of course, this is a surface mount situation. You have, this is close in principle to the flip chip that I mentioned before. Here you have a pin grid array. All the pins here can be mounted on the same surface of the board. You can see in this situation you can have a very high density of pins. Okay. Just one thing that I would like to mention that is very common now is what is called now system on a package. And in a system on a package, you typically have a sort of multi-die in the same package. For example, in this situation, maybe this is an extreme. You have several dies that are on the same substrate, and they are put in the same package. So essentially, in principle, you have a single package that, instead of containing a single chip, contains multi-chip which are put on a single board, a single substrate more than board. This is becoming more and more common because it allows you, on the one hand, higher integration, and on the other hand, for different functions of the system that you want to do, you probably need different substrate materials, and therefore it's useful to have separate dies for separate functions instead of having just one single die. Okay, we can stop here.